All right, let's do a couple more examples where we try to identify the appropriate test for convergence or divergence. And I've got two examples to work through in this video. The first one is a little messy looking. It's got 4 to the n plus minus 1 to the n times e to the negative 2n. And we will take that one first, and then the second one is n e to the negative n squared. All right, so let's remember our hierarchy. We first have the nth term test, which involves taking a limit as n goes to infinity. And let's see if we can apply that here. So we would need to take a limit of this term, and it might be helpful to rewrite this in a different way. And so I'm going to write this as 4 to the n plus negative 1 to the n over e to the 2n. All right, that looks a little better. And then that can even be simplified further. If we wanted to split it up into two fractions, we could have 4 to the n over e to the 2n plus minus 1n over e to the 2n. And since both of the denominators have this form e to the 2n and the numerators have an nth power, it's starting to look a little bit like something geometric. And in fact, if we apply one of our exponent rules, we can write this as e squared to the n plus minus 1 to the n over e squared to the n. And now that the numerator and denominator are raised to the same power, we can think of this as 4 over e squared raised to the n plus minus 1 over e squared raised to the n. And once you've got it in that form, the limit of an is a lot easier to calculate. Both of those ratios, 4 over e squared is less than 1, and negative 1 over e squared is less than 1. And so as you raise them to higher and higher powers, they're going to get smaller and closer to 0. So nth term test is inconclusive. And we're going to need to opt for another test. All right, let's try the nth term test on the other series. So we need to look at the limit as n goes to infinity of an, which we could write as n over e to the n squared. And unfortunately, that's an indeterminate form. Both the top and the bottom want to go to infinity. And so that's no good. But since it is infinity over infinity, we could apply L'Hopital's rule. And we'll get 1 over derivative of the bottom with respect to n would be, well, derivative of an exponential is the same exponential. And then we just need to multiply by the derivative of the inside, which would be 2n. And in this case, we'll see that we do get 1 over infinity, which is 0. So unfortunately, this is inconclusive as well. The nth term test failed in both cases. Now, you may feel like there are some similarities between these two problems. They both seem to have some sort of exponential. They both have some sort of function in the exponent. And so that may make you think that we're going to ultimately need the same methods here. But unfortunately, that's not necessarily always going to be the case. In fact, we're going to find that we need to use different techniques to actually evaluate whether these two series converge or diverge. So let's focus on the one on the left for the time being. All right, our next option is to see if this is a geometric series or a telescoping series. And given that we know that an is the sum of these two terms, which are constants raised to the n, it suggests that we can actually treat this as a geometric series. We have, so the sum that we're after can be written as the sum of 4 over e squared raised to the n plus the sum of negative 1 over e squared to the n. And I didn't specify in the problem, but let's assume that we want to go from 1 to infinity, or let's go 0 to infinity. Okay, in this case, notice the r value is 4 over e squared, which e squared, e is about between 2 and 3, and so the denominator is going to be a little bigger than 4. And so this is going to be less than 1, which tells us that the first one converges. And then the second one, we have r equals -1 over e squared, which, taking absolute value, we get something like 1 over e squared is going to be somewhere between 4 and 9. So that's still going to be less than 1. And so again, that one converges as well. And since they are geometric series, we could stop there if all we needed to know was what does the sum converge, but we can actually go a step further now and say exactly what it converges to. Here we have the constant is 1 in both cases. That means this converges to 1 over 1 minus 4 over e squared. And the second one converges to 1 over 1 plus 1 over e squared. And that's again because the sum started with n equals 0. If the sum started with n equals 1 or 2 or any other number, we would have to adjust it a little more by shifting the index or taking into account the missing terms. But for this problem, as it's expressed, that is sufficient. Okay, so identifying it's a geometric series took a little work here. We had to do some algebra to be able to see that actually it could be expressed as something raised to the n. But once we had that, it was a much easier problem. We didn't need to do any fancy integrals or partial fractions or anything like that. It was just a matter of recognizing that the r's were less than 1. All right, on to our second problem. Here we have n e to the negative n squared, or n over e to the n squared. That does not look like a geometric series. It also does not look like a telescoping series, and so we're probably going to need to use one of our comparison tests here. And the first one that's proposed is the integral test. So let's give that a try. Let's compare to the integral from, let's assume we're going from n equals, sure, let's go 0 to infinity. So integral from 0 to infinity of the function x e to the negative x squared dx. If we can show that that converges, then we'll know that our sum converges. And if we can show that that diverges, we'll know that our sum diverges. Assuming that our function is actually positive, decreasing, and continuous. All right. All right, so let's graph that function. And it does not look like it is decreasing. It's actually increasing at first. However, if we go out far enough, it does look like it's decreasing. It's just this first little bit where the function starts out increasing. And so, although technically we can't apply the integral test to the sum from 0 to infinity, we could apply the integral test to the sum from, say, 2 to infinity, where the function is decreasing. And if the sum from 2 to infinity converges, well, then we know that the sum from 0 to infinity must also converge, because you can't have divergence caused by just 1 or 2 finite numbers thrown into the mix. All right, so this is something where the integral test can still be applied. We just have to do a little bit of work to justify it. And we can justify it in this case by recognizing that it is positive and decreasing and continuous for x larger than 2. All right, so let's go back. Let's try to evaluate our integral now. This is an improper integral. So first of all, replace our infinite limit with the limit as b goes to infinity and plug a b in there. Okay. Now that integral looks like one where we don't necessarily know the antiderivative off the bat, but a u substitution might help. So let's define u equals not e. How about just negative x squared? Du would then be negative 2x dx, or we could say du over negative 2 would be x dx. And since we have a definite integral, it would be a good idea to change our limits. And so when x equals 0, we have u is going to be equal to 0. And when x equals b, u will be equal to negative b squared. Okay, so we can rewrite our limit. Limit from b to infinity of the integral from 0 to negative b squared of e to the u And then x dx would be du over negative 2. Now, it always makes me just a bit uneasy when I have my upper limit of the integral being lower than the lower one. And so I'm going to flip the order of the integral here. And the reason that makes me uneasy is just it's easy to lose track of minus signs. And so let's write that as the integral from negative b squared to 0 of e to the u du. And if we want to change the order of the limits, we need a minus sign, which can cancel out the minus sign from the negative 2, and we'll just have a factor of 1/2. Okay, that looks good. Now we can take the limit, or take the antiderivative rather. We'll have 1/2. Antiderivative of e to the u is just e to the u. And so when we plug in our endpoints, we'll get 1/2 e to the 0 minus e to the negative b squared. And as b goes to infinity, that second term is going to have larger and larger negative exponents. And so it's going to go to 0. And so the answer is just 1/2. Okay, so our integral converges. And what that means is that the sum converges as well by the integral test. All right, so 2 more examples in the books. We'll try one more batch of examples in the next video, and that will be it for chapter 10.3.